3, 2.
Hello everyone, thanks for coming to our second year presentation. My name is Moulton.
And my name is Dalipaj, and our presentation for today is on Culvert reinstatement with fish baffles for flood mitigation and fish migration. We would like to thank our faculty advisors and industry partner. First, our faculty advisor, Krista Taverner, and our faculty for this course, Alex Potiondi, Tommy Bragnolo, and Karen Campbell, and also our academic chair, Peter Oswald, as well as our industry partner, Darian Swinnemer from CBCL. So, by human infrastructure and waterways being together, so when human infrastructure is built and there's water paths going through it, culverts need to be built. When they are poorly designed, if the velocities can be too high and fish cannot swim through them, as it's not as high as their swimming speed. So this disrupts the fish population and the ecosystems.
The objective of our project is to design a culvert with an integrated fish passage for improved fish migration and eco-connectivity.
So this is a little summary on our project. Basically, we're going to reinstate a culvert by adding fish baffles into it, which can also be called as a fish ladder. What this does is it creates pools within the baffle, which leaves the fish resting areas, so they can jump through them and rest before they continue with their path. We will also take into account the water flows for the future water flows and focus on the flood mitigation. This is our selected site. It's in Antigonish, Nova Scotia, and it was provided to us by our industry partner. It's in Highway 104, and it's a 2.4 by 1.8 concrete box culvert that passes down the highway. We have outlined, this is the water path that flows through it. Our deliverables. So we will be delivering a detailed design drawings, which will include our existing and our proposed culverts, and also our road cross sections. A design report, which will include our flow calculations, our culvert sizing and type, and our fish baffle sizing and type, and the reason why we chose them. Again, a review of the culvert and baffle options and the calculations that made us choose them, and the analysis of the rainfall data and flow checks for the watershed. So before we get into the project more, what is a culvert? We can think of a culvert as a little tunnel that allows water to flow through it. I guess not literal always. So it's a structure that's under roads or railways, and similar obstructions, and it prevents flooding, erosion, and washouts. This is also good for drainage. On your daily commute, you probably see a lot of culverts if you pay attention on the roads, and this is because they're very important to the human life. They make our transportation efficient and possible even in bad weather conditions. But people forget about something very important.
Fish. Migratory fish populations have decreased 76% since the 1970s. This isn't just due to recreational and commercial fishing industries, but it's also from human infrastructure such as dams and culverts. It is found that the flow velocities through these culverts are exceeding the fish swimming speeds, causing them to not be able to make it along their pathway, which prevents repopulation. This affects ecosystems as other animals rely on fish as predator and prey, and it also affects economies as well for fishing industries. These are the options to aid fish migration. We have the open bottom culvert, embedded culverts, and baffled closed bottom culverts. The first option for the open bottom culvert, this is a great option for the ecosystem as it uses the natural riverbed and streams for fish migration. One problem about it is that when velocities exceed design velocities, the habitat can degrade and be damaged. The next option is the embedded culvert. This culvert, similar to the open bottom culvert, is a great option for the ecosystem as it uses the natural riverbed and streambed grades. It creates a riffle sequence within the culvert which has high and low points for the fish to be able to swim through and rest in the low points and continue through the high points to make it through the culvert. And once velocities pick up higher than design velocities within the culvert, it can transport the high points of soils to the low points of soils, which will smoothen out the inside soils within the culvert, which will increase velocities inside the culvert, making it harder for fish to migrate through them. Another thing for embedded culverts is that they are embedded to 40% of their total design width, which means that they lose a lot of cross-sectional area for the design flow calculations. And the final option is the baffled culvert. This is a great option for when we see slopes of river or stream beds greater than 5%, as this causes high flow velocities within these culverts. The baffles will slow down the flow through the culvert and create pools, which allows fish to jump from pool to pool to make it through their migratory path.
So we have selected a culvert with fish baffle additions for this project. This is because our site slope was higher than 5%, and to choose any of the other options except for the embedded, so the open bottom culvert, we needed something less than 5%. Meanwhile, with our embedded, again, the slope is too high, so the flow velocities can be also very high, and we don't want the fill to transport. Fish baffles, as we said earlier, create resting pools so that fish can rest before going through their migration paths, which restores their natural migration paths. Yep. This is a little illustration on what happens with normal culverts and culverts with fish baffles. So on this culvert, we have a high velocity here, which results in the fish getting stuck over here. And then on this culvert, we've included baffles, and they create these little resting areas with slower velocities, and the fish can jump through all of them. And we have a happy fish and happy ecosystem. These are the steps to designing a culvert with fish baffles. So the first one is data collection. The data collection includes LiDAR data, survey data, and hydrological data. Then it will be flow calculations, culvert sizing and type, fish baffle sizing and type, and the energy dissipation pool. So first, we start with data collection. We will start by processing LiDAR data. LiDAR data is laser data that creates a 3D of like the elevations in the whole world, and we will download them from the government and process them using ArcGIS. After that, we will import them in Civil 3D and also combine them with our survey data, which is provided to us by our industry partner. After that, we need to add the hydrological data. So when we talk about hydrological data, we can consider a few things. It'll be the watersheds, water paths, so basically all the water bodies that are in the site, or it can be rainfall data. The data that we will be collecting and downloading, will be the water bodies around the site. I input that into Civil 3D also to help us with our watershed, which is the area of the water that will flow through the culvert. And also the water path is the area from the beginning of the watershed, is the path from the beginning of the watershed till the culvert. Taking those into account, we will do calculations, and we will also take rainfall data into account for 1 to 100 year events. So what a 1 to 100 year event is, it's not that this intensity of the rainfall will happen every 100 years. It's just that there's a 1% chance of it happening in any given year. And we designed for this because of Halifax water guidelines, and also because it's the worst case flow scenario. So we have to make sure that the culvert can handle all flow scenarios. These are some flow calculations. So flow calculations are important to not over-design or under-design the culvert. If we over-design the culvert, it can lead to unnecessary costs. And if we under-design it, it can lead to infrastructure failure or the fish not being able to go through it. So these calculations we still have to research them through, because I'm sure that the baffles do change a few of them. But this is our design flow calculation. It's Q equals CI&A. C is the coefficient based on land use, I is the rainfall intensity, and A is the drainage area contributing to runoff, which is basically our watershed. Then it's our slope consideration. Our slope consideration will be our slope from this downstream controlled riffle elevation to our upstream elevation. This is just where the velocity is the highest, and that is where the velocity is the lowest. We will divide that by the length of that area, and that's how we get the slope. And for the flow velocity, it's just the Manning's equation, but I'm sure that this will change in our future research, and we will have to talk about that with our industry partner.
Culvert sizing and type. It is important to size culverts appropriately to ensure adequate flow. The DFO guideline specifies that we must use a minimum diameter of 1.2 meters or 1,200 millimeters to ensure adequate flow through these culverts, as the fish baffles take up an amount of the cross-sectional area, which restricts flow through the pipe. Typical materials that we can use for culverts is corrugated steel pipe, or CSP. This is used for durability. HDPE, or just plastic, can be used for flexibility, and concrete for strength.
This is our baffle sizing and spacing. So the baffles must allow for a minimum water depth of 100 millimeters above the notch to allow for the fish to go through them. And this is important because reducing velocities, it's important for the reduction of velocities, and that's the whole point, so the fish can go through them. This is our notch depth, which is the top of the elevation from the baffle to the top of the elevation from the water. And this is our drop between the baffles. So if you can see that line there, it's just the height difference between the previous and the following baffle. So this notch depth must be 50 millimeters bigger than this, as per DFO specifications, which is the Department of Fisheries and Oceans.
And finally, energy dissipation pools. This is a widened shallow area at the outlet of a culvert. It's used to dissipate the outlet flow velocities to prevent erosion and scouring of the nearby habitat. The width of the dissipation pools would be 2 times the diameter of the culvert, and the length of the dissipation pools would be 3 times the diameter of the culvert. The dissipation pool is formed with riprap stone to further prevent erosion and degrade the habitat. And there's 3 boulders placed in the center of the dissipation pool to also manage the velocities.
So that was our procedure, and this is our conclusion and future initiatives. So poorly designed culverts block the fish migration, which obstructs their migration paths. And our solution is to input fish baffles into culverts to reduce water flow and to make it able for them and restore their natural migration paths. Our research so far confirms that this is effective, and our future steps are conclude the data collection, start and finish our flow calculations and design, and also the report on the improvements that this brought. So what difference it was from the existing culvert to the proposed culvert.
Thank you for your attention.
Do you have any questions?